The agenda today, we're going to talk about what IPFS is. We're going to talk about the problems it's trying to solve. What is content-based addressing, which is kind of the way we address content in IPFS. We're going to talk about what a CID is, or a content identifier, how we talk about our data using identifiers. We're going to talk about how IPFS structures its data, and then we're going to have a quick demo about how that structure looks like using a visualizer tool that they developed. And then we'll just go into some brief notes about the routing, the network routing in IPFS, the privacy, some basic costs of using it, and then a demo I wrote over the weekend that leverages the IPFS to download Mina archives. And instead of using like Google Bucket, we can download Mina archives through IPFS instead. So yeah, if anyone has questions, I'm trying to go through it really fast, but if anyone has questions, I'm happy to answer. So what is IPFS? To give a definition of IPFS in one line, it can be described as a distributed system for storing and accessing files, websites, applications, and data in general. It works on a peer-to-peer network, which means that you're connected to a set of peers, and that's the medium you use to exchange data. It was created by Protocol Labs, which are the developers behind Filecoin. And to reference and like interact with the data that we upload to IPFS, it uses something called content-based addressing. And content-based addressing is this idea that normally when we want to like access our data, we go to a specific website or URL like Dropbox.com, and then we go to that specific location, and then we get our content. But in IPFS, what you do is you tell your data what's the data you want. Using kind of like a fingerprint, you take a hash of your data, and that serves as kind of like the way you talk about your data in the network. And we'll take a deeper dive into what content-based addressing is, but to get a good idea of what IPFS is trying to accomplish, I think it's useful to understand the problems that it's trying to solve first. So what are the problems that IPFS is trying to solve? Currently, when we want to get some data, we have to go to a website, and we kind of have to trust that that the authority running those servers are who they say they are. So if I uploaded a picture on Google servers, I'm kind of trusting that when I go to that picture later, Google's still hosting those or still running those servers and giving me the content I want. But you can imagine a scenario where a website gets hacked, and then that data that I originally had gets replaced with malicious content. And so there's that built-in trust in Google servers that allows this interaction to happen. It would be nice if we could just upload our data, and we upload our data to the network and not have to worry about the data being swapped out and just getting it from anyone who has it. Another problem is that information right now is not very resilient. The way information is stored and consumed on the internet right now has this problem of everything being centralized. So there's a massive amount of data being stored by cloud companies like Amazon and Google and Microsoft. And if they suffer a network outage, your whole application goes down, and there's not really anything you can do about that. Another problem with information being so centralized is that it's kind of prone to censorship. So governments and other authorities have this ability to block, and they have access to block networks and kind of decide what information can be easily accessed. And an example of this was in 2017. The Turkish government blocked access to Wikipedia during an administration because the administration said that Wikipedia was a threat to national security. And so what some people on IPFS did was that they just uploaded the content of Wikipedia on IPFS. And so it was still accessible since it's all distributed in a peer-to-peer way. Getting information is not very efficient. And what I mean by that is if I wanted to download a specific picture that I uploaded to Google servers, my device has to make a request and then make all those network hops to Google servers and then get that data and then bring it back. And that works fine. But then if my mom was in the other room and she really liked that picture and she wanted to have it on her client or her device, she has to go through the same steps, go all the way up to Google servers and then download that data. It would be nice if there was some sort of caching mechanism involved where if I already have the data, I can just give it to her without having her device go out to the network. I can just give her the data, and the protocol kind of supports that like peer-to-peer communication natively. Another problem is that there's no offline use. So you can imagine a scenario where we're all in a room together and we're working on some like collaborative software, like we're on a Google Docs, and the network goes down, like we don't have access to internet anymore. There are a lot of applications that don't really need this like way of talking to a centralized server to continue operating. We can kind of communicate through peer-to-peer, even if the network is going down. So we can form our local network and still use something like Google Docs in a peer-to-peer way. So we don't really need to like go out to the server. We can just form our own kind of network and just continue to use our products. And the data right now is, in today's web, is very mutable. So things like links can break all the time, and information that gets put on the network should be able to be accessed, even if you mutate or change your web page. So like applications like the Wayback Machine are kind of solving this problem by saving archives of web pages. So we can always see the information that's changed, and we have like a historical record of web pages. It would be really nice if we had a protocol that kind of like supported this built in, and we had that power really easily. So that brings us to what IPFS is. IPFS is distributed, meaning that when you add an IPFS, or when you add a file to IPFS, the protocol will split it into chunks and then distribute those chunks amongst your peers in the network. And so this means instead of going to like a central server to pull your data, you can talk to your peers and get these chunks really from anyone who has this data. And so this makes it more resilient to going down and more difficult to censor. IPFS is also immutable. So the way we talk about our data is through these like identifiers, which are cryptographic hashes. And so that means if you change your data in any way, the cryptographic hash changes. And so data, in a sense, is immutable. And if we want to update our data through IPFS, we go through like a versioning system, and we'll kind of like touch on that a little bit more in a bit. IPFS is verifiable. So meaning when you download a piece of data, you can kind of compute the hash of that data and check for yourself if that's the data that you really want. So this protects you from like downloading kind of malicious or incorrect data. And then IPFS also supports something called deduplication. And this is an idea of minimizing and downloading and computing similar or the same information twice. And so like an example of this is, let's say I had a text file that said hello world 300 times, and then I distribute that into the IPFS network. If I wanted to update that file and just add one more line, the content or the information that I need to download shouldn't have to change all that much, since it's just like one extra chunk that I added, adding this extra line. So if I download this updated file, I should just be able to download that extra chunk if I already have the rest of the data. So you don't have to go out and download the same image essentially twice if you're just updating a very small part of it. And we're going to go into a little bit more detail on that too. And then IPFS uses something that we touched on, which is content-based addressing. And this is the idea that you create a hash of your data, and this is kind of how you talk about your data in the network. So diving a little bit deeper into this, the web right now uses something called location-based addressing. And what location-based addressing is you're kind of saying, I want the cat picture at google.com/images/cat.png. It's sort of weird to talk about your data in this way, if you think about it. If you were to use this analogy to find a book in a library, you'd kind of be saying to the librarian, find me the book on the 4th floor on the 3rd shelf of the 2nd bookshelf. And you're not really saying like what book you want, you're saying where the book is. And this is kind of like analogous to how we're specifying like URLs to get our data. But there's a problem with this, is that there's no way to like verify that we're getting a cat picture just by specifying this URL. It could just easily be a picture of a dog. And there's no real way for you to know without downloading that data and then just checking yourself. So what IPFS tries to do is use content-based addressing. And what it means is you're saying, I want the cat picture that has the fingerprint, and then this is the content identifier that we have been talking about. It's this hash, this QM, and then this long string of characters. And so when we hash our data and we use this as an identifier, we can kind of talk about our data globally and uniquely amongst our peers, and kind of just retrieve it from anyone who has that data. So you can see an example on the left using kind of location-based addressing. If we want a certain picture, we go to the server that's hosting that picture and download it. But it would be nice if someone just like up here next to us had that data and we just specify to the network that we want it, we can just grab it from them. It doesn't really matter where it comes from. We're saying we want the data and that's how we get it. So looking at what a content identifier really is, like a CID, it all starts with the cryptographic hash of your data. So we start with a file and then we just hash it, and then that's really what it is, like the identifier. By default, IPFS uses SHA-2256 by default, and this kind of works well when we're talking about our data globally this way. But there's one problem. What if we want to use a different algorithm? Hashing algorithms can break, and we would like kind of like a future-proof way to talk about our data in this way. So the developers of IPFS, they came out with CID version 1, and it's just kind of an upgrade to the old content identifier. And so the difference is that we use something called a multi-hash, and a multi-hash is just a hash with just a little bit of extra information to talk about what kind of hash it is. It's just a little bit of extra metadata. And so with version 1, you can specify different hashing algorithms, and you can specify even different ways to encode your data. And the version 1 kind of format looks like, as you see, there's a content identifier version. We use a multi-codec, which is like the way we encode our data. And that's the DAG PB section of this image here. And that stands for Directed Acyclic Graph Protobuffer. And there's many different ways to encode your data. You can use JSON, for example. It's all specified in your multi-hash. And then we can also specify a different hashing algorithm like SHA-2. And then that 32 is just the length of the multi-hash. And then anything that comes after this is just the data, kind of like similar to what we were working with before. And in version 1, the content identifier looks like that string there, the BFYB, again, just like a long string of characters. So how does IPFS structure its data? So we talked about IPFS splitting data into chunks, but how are those chunks structured? IPFS creates something called a Merkle directed acyclic graph to represent your data. And I'll just call this DAG for short. And a DAG is just like a special type of Merkle tree. And it just can kind of point to the same child and have multiple nodes, very similar to a tree. And then to build this, it starts from the bottom up. And just to give like a visual representation, this is kind of like what like a Merkle DAG could look like. You can have like the top node represents like a file system, and you have your folder called pics. And then in this folder pics, you have one folder for your fish, one folder for your cat pictures, and then the leaves are the content themselves. And you can see that it kind of structures like in this child-parent kind of way. And the idea with IPFS is that each node will have its own content identifier. And that makes retrieving these files very easy. The example with deduplication, for example, I could download the picture of fish and the folder with fish and the folder with cats from two separate peers because we're just referencing them by content IDs. And so this gives us like this very efficient way to parallelize our downloads amongst our peers. So why use a Merkle DAG? Merkle DAGs are cool, but like, what do they give us? Like, why did IPFS choose Merkle DAGs? So firstly, Merkle DAGs are verifiable, and that means that an individual who retrieves data from that content address can always compute the content address for themselves. So they can always check if the information that they're getting is truly what they're intending to get, and it's not swapped out with anything malicious. Merkle DAGs are distributed, and so this makes it really easy for distributing large data sets. When we're retrieving data encoded in a DAG, we can leverage the fact that things can be downloaded in parallel. So this means you can download things in a much faster rate because we're not downloading all our assets from the same source. We can specify one peer and another peer to give us two different sets of information that forms the entire DAG. So it gives us that really cool parallelization in downloading files. And then finally, Merkle DAGs offer deduplication, and that's like basically encoding redundant sections of your DAGs, and then you can link back, when you update some content, you can link back to the previous DAG. So this is how IPFS accomplishes versioning your data. When you update your data and then you create a new content identifier, the DAG that's created can actually link to other DAGs, and so you're not recomputing all the chunks again. You can just link back to one that was previously updated, and so you're really saving on downloading the same picture twice, essentially. So I have like a quick demo just to really give a look into like how this looks like, because I'm a visual person. I think it's a little bit helpful. IPFS came out with this DAG visualizer tool. You can find it at dag.ipfs.io. You can drop like files in here and it'll render a DAG for you. And so I just want to show you what this deduplication looks like. I have this hello IPFS text file and this hello text file. So what this hello text file is, it's just a text file that just says IPFS hello 300 times. Pretty boring file. If we drop it in and see what the DAG looks like, these bottom leaves are the chunks. This is the data that the file is encoded in. And then we have this top node here that we use to like download all these chunks. So you can see that, I'm not sure if you can see this well, but each block has its own content identifier. And then the top node has its own content identifier too. And so it creates this DAG for us. And let's say I have this other file here called IPFS hello updated, which is essentially the same file, IPFS hello 300 times. And I have this extra line here that says IPFS hello updated. So the information is essentially the same in these files. So if I drag it in here, you'll see what IPFS does. It's a little hard to see, but I'll demonstrate this real quick. IPFS will update the DAG and create this extra node here that references the same content as our previous DAG. You can see that it's all linked in the same way, but there's just this extra chunk here, which is just that extra line that we added. And so you can see that when we add and update files or information, we can link back to previous DAGs, and this is what it means to for deduplication. If I already downloaded this DAG, I already have all this content here, and so if I download this DAG, I get the updated version of it. I just need this chunk here. I don't need to download these again. I already have them stored. So yeah, that's what the Merkle tree looks like, or the Merkle DAG looks like. Oh, cool. So we talked about content IDs and how we like reference data, but there's like a problem with this. Let's say I have a website and I'm using IPFS to distribute my website content, like my HTML code, my CSS code, and the JavaScript code. All of it's like retrieved through IPFS. That code or that content is addressed through that content identifier. And so if you go through IPFS and you download my website and you view it in your browser, you use the content identifier. But if I make a change to the website, the whole identifier changes. And there's no way for people to know really when that changes. So if you're used to just going to my website at a certain content identifier and I update it, that content identifier doesn't point to the new website. So we kind of want a way to like talk about content identifiers, but not reference them directly. And so the first way we can kind of do this is using something called IPNS, and that stands for Interplanetary Name System. And the way it works is you set up a public key with the node that you're working with, and then you create a hash out of that public key, and then that hash is associated to the content that you want to publish. So you can see here, I have the command IPFS name publish IPFS in this path here. If I wanted to map it to an IPNS, like the key that I already have, you use this command, and then if you go to the hash instead, the K51QZI, that content will always be updated. And so you can, as like the maintainer of your content, you can update your website, and users can just use that hash of your public key to view your content instead of viewing the CIDs themselves. So kind of gets away with updating like that website, for example. Another way that we can do this is using something called DNS link. And this is the idea of like mapping DNS records to a specific IPFS CID. And the cool thing about this is you can kind of change the DNS records of your website anytime if you have access to it. So if I publish my CID and I updated it, and I get that new CID, I can just go into my like cloud provider or like DNS provider, change the DNS record to point to this new IPFS address, and then we can use that domain name to always kind of point to the updated content that we have. So how are like files found in IPFS? This is very brief. I'm sure like people here know much more about this than me, but IPFS uses something called a distributed hash table, and it's kind of just a set. It's just a table of who has what. So when you want to like get a CID from someone, you talk to this. You use this distributed hash table, and you kind of see who, like Ozzy. If I'm looking for QM Foo, I go talk to Ozzy, who has the content I want. And to like give an example of how we access content in IPFS, there's this link here, which is a IPFS gateway, which lets us like talk to IPFS in the browser through HTTP. If you stick this in your browser, this link here, you can, I have it open already, I can post it in the chat. If anyone's interested, if they want to try themselves. If you open this, you should see this in your browser. I'll refresh here so it works. Yeah, we can like reference our content in this kind of way, talking to the browser. We just need the content identifier, and it'll bring us the content that we want through this hash table. So how do we persist data on IPFS? Data is immutable, but that does not mean it stays up online forever. So someone has to be serving that content on the IPFS network, and if someone stops serving it, that content goes down. So to persist your data on IPFS, you have to pin it. And pinning is this mechanism that allows you to tell IPFS to keep a given object around. When you interact with an object, IPFS has like a fairly aggressive caching mechanism, and it'll keep an object around on your node for a certain amount of time when you interact with it, but then it'll eventually garbage collect it and drop it. So this means after some amount of time, if you don't pin your data, it'll get garbage collected and essentially just stop being served. So to continue to serve our data, we have to pin it. And there's a kind of like different ways to set up running an IPFS node. We can do it ourselves. We can just download the IPFS software and just run the CLI tool and run it on their client and just serve the files locally on our machine. And this is kind of similar to like running BitTorrent. So you can pin your data and just continue to participate in the network. You can use third-party pinning services. So this, for example, is kind of like a managed system. There are services and companies that run dedicated IPFS servers, and they'll pin and run the nodes for you. So this is kind of like a managed solution. You kind of just send like your data through an API endpoint, and then they'll save it on their infrastructure and just pin it and serve it for you. And so that's a pretty convenient way to serve your data through IPFS. And then there's Filecoin. Filecoin is a little interesting because it's meant as kind of like a data retrieval or like cold storage kind of mechanism for your files. So the integration is a little confusing. The Filecoin and IPFS network are two separate networks. So they don't really like know about each other natively. There are companies and products that are coming out that integrate these two together. So the idea is you send some data through to this company, for example, that's offering this kind of solution. They will pin your data on IPFS, and then they'll create like a deal on Filecoin to store your data for long-term storage and replicate it. So IPFS is kind of like serving your content in this hot loaded kind of way, and then Filecoin will replicate it and store it for permanent storage. This is kind of new and still being worked on. The technology around this is pretty cool, so I'm excited to see how it progresses. If you were to use one of these services, how much does it cost? Pinata is a third-party service, and they have like a pro plan for $20 a month. That's 100 gigabytes of bandwidth per month, and then you pay an additional 5 cents per gigabyte. There's another third-party service called Textile, and they give you the first 5 gigs free with an additional 3 cents per gigabyte. And to give an idea, like a comparison of how like a centralized kind of solution would look like pricing-wise, Amazon S3 gives you the first 10 terabytes of data transfer for free, but then you pay an additional 7 per gigabyte. And these costs are for data transfer. They're not for storage. Simply just the bandwidth you're paying for people downloading this stuff. So just brief mention on privacy. Traffic between nodes are encrypted, but that does not mean that the data you upload is encrypted. So the data you serve is public, and once you throw it out there, anyone can kind of access it. So if you want to keep your data private, you have to encrypt it first. If you encrypt your data and then upload it to the IPFS network, even if someone has it, no one really can really make sense of it except you as the person that's able to decrypt it. So he can later just download and use this data normally. And all traffic on IPFS is public too, so anyone can kind of set up like a monitoring service and see what traffic is moving around into who. So this is something just to keep in mind if we were to use IPFS. All of this traffic of like who's getting what and all that stuff is public and in the open. And so I have a section just briefly showing like how to use it, what's the code like. So if you download IPFS and use the CLI tool, you can see here, I had like a text file, it was hello.txt. And if you want to add IPFS, you want to add this hello.txt to the IPFS network, you just do IPFS add, and then it'll return you the content identifier. And then you can use the cat command with the specified content identifier to get that data. And very simple and pretty easy to use. If we wanted to use JavaScript, there's software that we can use, like a library, to just create a node, specify some data. It can be a string, it could be JSON, it could be just like a proto buffer, it could just be any kind of encoding you really want. And we can just do .node.add with our data, and then that will publish our data to the IPFS network. Very easy to do from a developer experience. And so just to demonstrate this, I have this link here. I'll post this too. But the idea is it's a website that pulls Mina archives from Google Bucket and then throws them up on the IPFS network so that when you visit this website, you're actually downloading the Mina archives through IPFS and not Google. And this is just done with that JavaScript tool that we looked at. So I'll just post this here if anyone wants to take a look at this. And the idea is it's just a very simple website. It just has some Mina archives. And you can see here, we have the content identifier for a certain Mina archive. I display the origin. So this is the original Google Cloud or the Google Bucket link to get this archive. And there's a timestamp, and we can just download an archive as we would normally. It's very easy to use. Sometimes there's a failed network error. I'm not sure why this happens. I think this is something to do with IPFS because I've seen people complain about this, but if we just resume that download, it'll continue. And you can see that if we open this up, this is the SQL that we upload to IPFS, or sorry, to Google Cloud, but it's served through IPFS. So setting up IPFS is pretty straightforward. It's pretty easy to use. There are some kinks because it's very new and things are being improved, but yeah, that's the basic premise of it. And that kind of concludes my talk on IPFS.